Okay, so because I am out of town, I will be doing at least one of these, likely two. Each one should be running about an hour. This will be posted up on Canvas. Of course, by the time you're seeing this, it's already posted on Canvas. I don't know why I just said it would be posted up on Canvas. So what I'm going to do is I'm going to go through a quick review of what the problem was, why we need to solve the problem, the way that we do, and then I'm going to talk about an alternative method to actually solving it. This thing can actually focus worth a damn. Okay. So, recall the problem was to maximize utility that spans an infinite horizon, meaning we've got one representative agent who lives forever with log utility. So the utility function is the log of, or the natural log of consumption weighted by a stationary discount weight. So what this would look like expanded out would be like this. For the first period is the natural log of CT. The second period is beta times the natural log of CT plus 1. Third period is beta squared times the natural log of CT plus 2, and this goes on for infinity. So this is the maximum, or this is the utility that we want to maximize that runs over an infinite horizon. I'll keep that there for now. Remember when we had a constraint? Let's say we have constraints. The first constraint we have is a resource constraint. It says if we have output Y, output can be split only between consumption and investment. So if output were 100 and we consume 20, that means that we have to be investing 80. The sum of consumption and investment can never exceed output. Right? But we also have functional form for output, which is A times KT to the alpha, where alpha is less than 1. We've also got functional form for this IT, which is referred to as the law of motion of capital, and it's the flow of capital over time less depreciation. All right, if I wanted to rewrite this guy out for a second, and give me that. Right, so the larger the difference is between what tomorrow's capital is, KT plus 1, and today's capital is, right, that difference increases, investment's going to go up. But we also need to account for the amount of capital that's falling apart, which is delta times KT. All right, so this is our law of motion of capital. And what we do let's go ahead and label these equations 1, 2, and 3. What we're going to do is we're going to substitute equations 2 and 3 into equation 1. So if y is equal to at times kt to the alpha, I just substitute that in for y. Right. So all I've done so far is just substitute equation 2 into equation 1. I haven't done anything with equation 3 yet. Now it's time to play with equation 3. Get that. So now this is a constraint that we can use if we want to use some form of substitution in our constrained optimization to maximize this problem here. So how do we do this? Well, if you recall from last week when I scared the living daylights out of everybody, apparently lost my towel that I was going to use to clean off the board, which means I just have to use this really shitty dry erase marker, which doesn't really erase very well. So we've got this problem. So far, nothing new, nothing radically different than what we've seen so far. If you've been awake in class for even 5 minutes, nothing about this should be radically different. I literally just rewrote something I put on the board just a minute ago. And I'm going to say I'm going to maximize that subject to at times kt to the alpha equals ct plus kt plus 1 minus delta kt. This is the constraint that we've got so far. Right now, if we remember what we talked about last week in class, if I found a way to substitute something in for ct into this utility function, then I was in good shape. So how do I do that? Well, if I've got a CT in here, and I've got a CT in this constraint, if I solve the constraint for CT, then I can plug what's in the constraint into CT in this utility function. Right, so I'm going to be subtracting kt plus 1 minus delta kt from at kt to the alpha, right? So basically what I'm doing is I've got output minus investment. So if I'm subtracting investment, I got to distribute a -1 through here. I'm going to get rid of that parenthesis, get this parenthesis gone. And it's going to give me that. I'm going to distribute that -1 through the whole thing, get that guy right there, and now this is my constraint. And the nice thing about this constraint is C being a function of a bunch of other stuff. But if this other stuff is equal to C, then I can plug that in up here. So this is the constraint that I'm going to be plugging in for CT in my objective function. But there's a cool way that I can rewrite that objective function if we remember. Right, so this is the method that I talked about in class that I will be reviewing one more time. I will go over how to do it. I will do one more example with it, and then I will show an alternative way to do it. And if there's time permitting, I'm going to also try to talk about how to express the general equilibrium of the model and how to find the steady states of the model. So the method that we learned in class, we will call this method 1. Method 1 is to use a Bellman equation. Right, this method is what's known as dynamic programming. Wanted to use that Bellman equation, we had to figure out a way to express this guy here recursively in terms of something that would separate or reduce an infinite horizon model down to a 2-period model. And basically, thanks to calculus 2, thanks to this beta here being less than 1, it guarantees we've got convergence of this infinite geometric series gives us something like this. Now I'm expressing it in terms of consumption for right now, but we'll be doing away with that in just a minute. This right here, V of CT equals a natural log of CT plus beta times V of CT plus 1, is equivalent to this expression right here. These two are the same thing. Alright, but now let's say what I want to do is instead of doing it in terms of CTs, I'm not going to get anything that particularly interesting if I were to just differentiate this guy with respect to CT. There's not that much going on at the moment. Alright, so what can I do instead? Well, what I can do is I can substitute this constraint in for CT right here. Now please forgive the small board space that I've got. Normally I've got about 30 feet of board in the classroom to ramble on incessantly. This makes it a little bit more difficult. So say from the Bellman equation where we had V of CT equals the natural log of CT plus beta V CT plus 1. From that Bellman equation, this, what I can do is I can substitute the right-hand side of my constraint into CT up here. Like this. Now, if we recall, the reason that we're doing this, aside from the fact that we can get slightly more interesting stuff out of it, the economic reason behind why we're doing this is that if we choose capital optimally, and we can figure out what investment's going to be, we figure out what output's going to be. So if we optimize capital, we're optimizing output. If we're optimizing output, we are optimizing consumption. Capital comes first, everything follows from that, right? So I'm going to erase some of the stuff up top, move this guy up top, so we're going to need a couple of lines that we probably don't have on this board in order to actually really be able to express what's going on here. Gives me this. All right. Now what I need to do is I need to take my first derivative. Or as we call them in economics, to sound fancy, because as economists we love to just use fancy words to describe things that really aren't that particularly fancy, to make people think they are fancy, to scare them into paying us more money. I need my first order conditions. Right, so what is the first order condition I get? Well, what I need is I need a partial derivative kt with respect to kt plus 1. All right, well, we remember our chain rule. The partial derivative of this guy here with respect to kt plus 1 is 1 over this jump, because we got the natural log of stuff. So the derivative of the natural log of stuff is 1 over that stuff times the derivative of what that stuff is with respect to the variable of interest. The variable of interest here is kt plus 1. So if we look at at times kt to the alpha, if we were to just look at this individual term and go, what's the derivative of that with respect to kt plus 1? 0. What's the derivative of negative kt plus 1 with respect to kt plus 1? Well, the derivative of kt plus 1, or negative kt plus 1, with respect to kt plus 1 is negative 1. It's the leading coefficient. Well, that looks infinitely worse than it did before. We'll fix that in post. Or not, because I'm lazy and don't know how to fix it. I really just don't know how to fix it. We'll assume, we can pretend that I'm lazy, but it's just that I don't know how to fix this. What is that rule again? Never attribute to malice what can easily be attributed to incompetence. This is that rule in action right there. So that part's done. All right, that first term in the Bellman equation has been differentiated with respect to kt plus 1, so we move on to the next term. And I'm going to get beta times the partial derivative of v kt plus 1 with respect to kt plus 1. All right, but we're maximizing our utility. Thus our first order conditions are implying that we are setting this equal to 0. Because recall, any function's derivative set equal to 0 is going to imply either a maximum or a minimum of that function. Generally it's up to the, we'd say economist, but ultimately in this case the mathematician, to determine whether it's a maximum or a minimum by evaluating the second order conditions. But because this is intermediate macro and this is not graduate level macro, I am assuring you that we are getting a maximum, so you don't have to do any of the second order shit to worry about here. This is getting us a maximum. All right, so let's clean this up at least a little bit. I am currently in a hotel. That was clearly somebody using the bathroom. If that isn't horrifying for you to imagine how it is for me. I'm a lot closer to it than you are. So this is what I get. We recall this junk in the denominator is equal to this junk here is equal to CT. So to just shorten everything down, I just substitute a CT back in there. So I've got 1 over CT times -1 plus beta times the partial derivative of v of kt plus 1 with respect to kt plus 1 is equal to 0. Right? And this is where the shit kicker comes in, because we don't know what dv kt plus 1 d kt plus 1 is. Right? We know what dv kt d kt plus 1 is. But if we look, right, we're taking a partial derivative of this function kt with respect to kt plus 1 here, and over here we're taking a derivative of the function of kt plus 1 with respect to kt plus 1. The time subscripts aren't the same. Well, they're the same here, but they're not the same here. So what we have to do is we got to figure out a way to get this guy. And we're not going to get this guy by trying to get this and update it one more period, because the time subscripts aren't the same. We need something where the time subscripts are the same. So what can we do? Well, we could start by going, okay, well, I could just get dvkt dkt plus 1. So we'll say problem. And the problem is that we don't know what dvkt plus 1 dkt plus 1 is. we've got a little frowny face, and I'm going to give him glasses this time. He's got some really creepy glasses, and his eyes are super far apart. It's like nerdy Britney Spears. Anyway, that bad joke, fix that one in post too. Oops. There we go. Regular eyes like I draw in class. So we don't know what that is, but we might know what? Like Billy Mays. But wait, there's more. Which is exactly what he said after Farrah Fawcett and Michael Jackson died. So we don't know what this guy is. We can get that. We can get dvkt dkt. Right, and if we look at our partial derivative notation, we will see that this and this aren't the same. Why aren't they the same? If we look at the denominator, it's not going to be identical. We don't know what. If we take this, we're going to get something we're not aware of that we don't know. But if we take this, we can. Right, so if we're taking the derivative of dv, taking the derivative of v of kt with respect to kt, we will get something that we can figure out analytically. What is it? Well, what we do is we just go through v of kt. So we go through this equation here again. Only instead of taking the derivative with respect to kt plus 1 like what we got here, we're doing it with respect to kt. So we're going to go here term by term and see where we get something with respect to kt. Now remember, the derivative of the natural log of anything is 1 over whatever that anything is. So we're going to keep that nice and easy. Like that. All right, so that's going to be the same. Nice. Easy. Fun. For me. Hopefully fun for you. All right, but now we're going to take the derivative of the inside of that. So what's the derivative of this guy with respect to kt? Well, just multiply that by at kt to the alpha. So we have to differentiate this guy with respect to kt because there's a kt in here. What is that? Well, it's going to be alpha times at kt to the alpha minus 1. All right, that is the marginal product of capital for the firm. We discussed this during the solo model. All right, that's telling us how productive one additional unit of capital is going to be. Now, in a world where capital didn't fall apart, that would be all that we had to worry about. But capital does fall apart in this world. Capital falls apart in this world, so we need to be able to account for that. How do we account for that? Well, we just keep taking the derivative. We'll see where we get. Minus kt plus 1. Is there a kt in kt plus 1? The answer to that is a big whopping no. So that differentiates away to 0. So now what we got left is that plus 1 minus delta kt. There is a kt in there. What's the derivative of 1 minus delta kt with respect to kt? Well, it is simply 1 minus delta. And this is what we get. Now let's simplify this guy just a little bit more. If we have this then we can rewrite this as 1 over CT times alpha times AT KT to the alpha plus 1 minus delta. All I did was just substitute CT back in for that resource constraint that I plugged in for CT in the Bellman equation up top. So this is what we got so far. And now what I'm going to do is I'm going to update this guy 1 period. Why am I going to update it 1 period? Because it's going to give me exactly what I want, dV of KT plus 1 with respect to KT. So updating that guy 1 period. Gives me that. So now I've got dV KT plus 1, dKT plus 1, and I know what that's equal to. What's that equal to? Well, it's equal to 1 over CT plus 1 times the marginal product of capital less depreciation. So we got to tear through all this math. Where do we see a dV KT plus 1, dKT plus 1 somewhere? Oh, we see it right here. So let's fix that. This. And of course I made 2 mistakes because we all are prone to mistakes. I forgot to add a minus 1 to the exponent here. Forgot to add a minus 1 to the exponent here. And the marginal product of capital is alpha times AT KT to the alpha minus 1 plus 1 minus delta. So that is my mistake. Please make sure to correct that mistake. But this is what we get. And we have to set this sucker equal to 0 if we want to maximize it, right? So let's go ahead and erase this. Save some room again. Now, what I'm going to have that 1 over CT times negative 1 plus beta times 1 over CT plus 1 times alpha times AT plus 1, KT plus 1 to the alpha minus 1, plus 1 minus delta, and that's equal to 0. So if I just add CT to both sides, gives me that. 1 over CT equals beta times 1 over CT plus 1 times alpha AT plus 1 times KT plus 1 to the alpha minus 1 plus 1 minus delta. All right, and this is our Euler equation. Right, and what this says, this part here is the marginal utility of current consumption. Recall, economists are always thinking on the margin. Rational people always think on the margin. We are being rational. We're assuming this household is being rational, thus they are thinking on the margin. So what is the right-hand side of the equation? Well, the right-hand side of that equation is the marginal utility of future consumption discounted by personal preferences, which are beta, and market conditions, which is the marginal product of capital. So what this says is that at the optimum, the household is equating their marginal utility of current consumption with the marginal utility of future consumption discounted by preferences and market conditions. Okay, that sounds a little too economical. This says that the household at the optimum is figuring out how much to consume today versus how much to consume tomorrow based on how patient they are and how rewarding the market is for their patience. Beta is a measure of how patient we are. It's a measure of how much we care about tomorrow relative to today. Right? So that's almost like a punishment of sorts. But this marginal utility of future consumption, or not marginal utility, sorry, the market conditions are a benefit. This is a reward. The more patient we are, right? Yeah, it's going to punish us today because it means less consumption today. But if we decide to be a little bit more patient, we get rewarded by this much for each additional unit of consumption that we choose to consume tomorrow instead of today. So for every single unit of output that we invest rather than save, this is the amount that we get to consume tomorrow as a result. So that's our Euler equation. Now, before I move on to